You've probably heard of engines that dominate racetracks or set speed records. But what if I told you there's an engine that was literally too tough to die, one that laughed at conditions that would destroy normal power plants? This is the story of how Chrysler took technology designed to power 30-ton tanks through battlefields and created something that would quietly revolutionize everything from industrial equipment to marine applications. An engine so overbuilt, so ridiculously robust, that it made conventional designs look like toys. I'll picture this. It's 1951, and a construction foreman in Michigan is watching his third engine failure of the month. The job site is brutal. Concrete dust everywhere, temperatures swinging from freezing to scorching, equipment running 18 hours straight with minimal maintenance. His dozers and pumps keep breaking down, costing thousands in delays. Then someone mentions this new industrial engine Chrysler's selling, something about it being based on a tank motor. The foreman laughs. A car company making industrial engines from tank technology? But desperation makes people try anything. 6 months later, that same foreman is calling every equipment manufacturer he knows, telling them about an engine that hasn't stopped running once. Not once. While everything else on the site has needed rebuilds, this bizarre Chrysler power plant just keeps grinding away day after day like it's barely working at all. This is the story of the Chrysler A57 Multibank and its civilian descendants, engines that weren't the fastest, weren't the most powerful per cubic inch, and definitely weren't the prettiest. But they possessed something far more valuable, the ability to run forever under conditions that would murder any other engine. These weren't just tough engines. These were engines that redefined what tough meant. To understand why Chrysler's tank engines became legends of reliability, we need to travel back to 1940. America hasn't entered World War II yet, but the military sees it coming. The Army needs tanks, lots of them, and they need them fast. The problem? Tank engine production is a bottleneck. The radial aircraft engines typically used in tanks require specialized facilities and skilled workers that are already maxed out building engines for planes. Dan Ninian and the Army approaches Detroit. Can the auto industry help? Most manufacturers propose modified versions of their biggest truck engines. But Chrysler's engineers, led by a man named James Zeter, have a different idea. Instead of scaling up one engine, why not combine multiple smaller ones? Engines they already know how to mass produce by the millions. Here's where it gets interesting. Chrysler doesn't just slap some engines together, they create something unprecedented, the A57 Multibank. Take five inline 6-cylinder engines and arrange them in a star pattern around a central crankcase. Each bank is essentially a complete Chrysler Flathead 6, the same basic engine that powered their cars and trucks. But when you combine 5 of them with a common crankshaft, you get a 30-cylinder monster displacing 1,253 cubic inches. That's 20.5 liters for those keeping track. The configuration was insane. Looking at it from the front, you'd see 5-cylinder banks radiating out like a star, one pointing straight up, 2 angled up at 45 degrees, 2 angled down at 45 degrees. Each bank had its own carburetor, its own ignition system, its own water pump. It was complexity multiplied by 5. But here's the brilliant part. If one bank failed completely, the engine kept running on the other 4. Lose 2 banks? Still running. This wasn't just redundancy, it was redundancy with attitude. Specifications were modest by tank engine standards. The A57 produced 470 horsepower at 2,400 RPM. Compare that to the Ford GAA V8 that powered other Sherman tanks. 500 horsepower from just 1,100 cubic inches. On paper, the Chrysler looked inefficient, too complex, too heavy, too many parts. Critics called it what the engineering nightmare, was the parts counter special, what and worse. But those critics were missing something crucial. West the A57 was designed with one philosophy: survive everything. Every component was overbuilt. The crankshaft was a massive forging that could handle far more stress than the engine would ever produce. The connecting rods were sized for twice the load they'd ever see. The cooling system had capacity for days of high-temperature operation. Even the oil system was designed with multiple pickup points so that extreme angles, like a tank climbing a 60-degree slope, wouldn't cause oil starvation. But the real genius was in the execution. Each of those 5 engine banks was a proven design that Chrysler had been building since 1924. They knew every weakness, every wear point, every failure mode. The Flathead 6 was simple, understressed, and fixable with basic tools. No overhead valves to adjust, no complex valve trains to maintain, just solid, simple, brute force engineering. And the Multibank went into production in 1942. Chrysler's Detroit tank arsenal started churning out Sherman tanks powered by this mechanical mutant. The factory was a marvel itself. At its peak, it could complete a tank in 4 hours. The A57 Multibank powered the M4A4 Sherman variant with over 7,500 produced. These tanks were primarily sent to British and Commonwealth forces, who had specifically requested them after testing showed something remarkable. The A57 was virtually indestructible, and British tank crews in North Africa discovered what Chrysler's engineers had built. In the desert, where sand destroyed engines faster than German shells, the A57 kept running. The Multibank design meant that sand infiltration that would seize a conventional engine might only affect one bank. The massive cooling capacity meant it could handle 120-degree desert heat while climbing sand dunes. The overbuilt bottom end could handle the worst abuse a teenage tank driver could dish out. One British tank commander reported running his M4A4 for 72 hours straight during the pursuit after El Alamein. No stops except for fuel. The engine temperature barely moved. Oil pressure stayed rock solid. Meanwhile, tanks with other engines were falling out left and right with overheating, seized bearings, and thrown rods. The Chrysler just kept grinding forward. But here's where our story takes an unexpected turn. The war ends in 1945. Thousands of these tank engines are suddenly surplus. Most military engines got scrapped or forgotten, but not the A57, because someone at Chrysler realized what they had created wasn't just a tank engine, it was possibly the toughest power plant ever built. And American industry was about to boom like never before. The transition started quietly. Chrysler's industrial division took the basic Multibank design and began adapting it for civilian use. They didn't need 5 banks for most applications, so they developed derivatives using the same philosophy: massive overbuilding, proven components, reliability over everything else. The first customers were oil fields, marine applications, and heavy construction, places where engine failure meant disaster. The marine version became legendary almost immediately. While other marine engines required rebuilds every season, the Chrysler industrial derivatives would run for years. Commercial fishing boats that operated 20 hours a day found these engines would outlast everything else on the vessel. One documented case involves a shrimp boat operating in the Gulf of Mexico that ran its Chrysler industrial engine for 11 years without a major overhaul. That's approximately 60,000 hours of operation. The captain only rebuilt it because he was selling the boat and wanted everything fresh for the new owner. The mechanics who tore it down found the bearings still within factory specifications. The construction industry discovered something similar. Chrysler's industrial engines, based on the tank engine philosophy, were going into pumps, generators, and compressors. These weren't sexy applications. Nobody was bragging about their water pump engine at the bar. But project managers were noticing something. The equipment with Chrysler power never went down. Let me put that in perspective. A typical construction site in the 1950s might have a dozen pieces of powered equipment. Statistics from the era show that operators expected roughly one major mechanical failure per week across their fleet. That's lost time, lost money, emergency repairs in terrible conditions. But sites using Chrysler industrial engines were seeing failure rates drop by 80%. One engine could do the work of three because it never stopped running. The technical reasons were fascinating. That massive displacement meant the engine was always loafing. Running a pump at 1,800 RPM that needed 100 horsepower, the Chrysler engine could make that power at 40% throttle with the torque curve so flat you could balance a nickel on the block. No stress, no strain, just endless, effortless power. The cooling system designed for desert combat, it laughed at civilian duty. The oil system built for 60-degree tank climbs, it kept perfect pressure no matter what angle the equipment sat at. But the real secret was something deeper. Chrysler had accidentally created the perfect industrial engine formula. Start with components proven over millions of miles. Overbuilt everything by a factor of 2. Designed for the worst conditions imaginable. Then put it in applications that were easy by comparison. It was like using a sledgehammer to drive finishing nails. Massive overkill, but it worked every single time. The competition couldn't figure it out. General Motors had their Detroit Diesel series, sophisticated two-strokes that made more power per pound. Caterpillar had their own designs with better fuel economy. On paper, the Chrysler engines looked obsolete. Too heavy, too thirsty, too simple. But paper specifications didn't matter when you were stuck in a Louisiana swamp with a failed water pump, losing $10,000 a day. And in real-world testing revealed the difference. In 1953, a construction company in Alaska conducted an inadvertent torture test. They had 3 identical pumping stations for a pipeline project, one with a GM engine, one with a Caterpillar, one with a Chrysler Industrial. The temperatures hit -40. The operators, trying to keep the pipeline from freezing, ran all 3 pumps continuously for 6 weeks. The GM engine failed after 8 days when the 2-stroke ports carboned up. The Caterpillar made it 3 weeks before a head gasket let go. The Chrysler? Still running when spring arrived. They changed the oil twice. That's it. And that's the engine's reputation spread through industrial America like wildfire, but not through advertising. Chrysler barely marketed these engines. They spread through word of mouth between operators, mechanics, and project managers. Get the Chrysler if you want to forget about it, because it's that ugly as sin, but runs forever. It costs more up front, saves you a fortune in downtime. Nor in the technical specifications tell only part of the story. The industrial versions typically displaced between 250 and 400 cubic inches per bank, depending on application. Power outputs ranged from 80 to 200 horsepower, not impressive for the displacement. But torque figures were extraordinary. The 331 cubic inch Industrial 6 produced 340 pound-feet at just 1,200 RPM. That's the kind of grunt that would pull tree stumps out of the ground or drive a concrete pump all day without breaking a sweat. The engines used flathead designs long after overhead valves became standard. Critics called them antiquated. But flatheads have advantages in industrial applications. No rocker arms to brake, no push rods to bend, no valve adjustments needed. The valves sat in the block, protected from damage, easily accessed for service. Carbon buildup that would destroy overhead valve engines just made flatheads run a little rougher. You could literally run them until they wouldn't run anymore, rebuild the heads in an afternoon, and get another 5 years. The cooling systems were spectacular overengineering, water passages large enough to stick your thumb through, radiator capacity sized for Death Valley in August while towing a house, water pumps that could flow enough coolant to fill a swimming pool in an hour. One operator reported running his engine with a cracked block for 6 months. The cooling system had enough reserve capacity to handle the coolant loss. He just topped it off every morning and kept working. Dust and lubrication systems followed the same philosophy. Oil galleries you could nearly crawl through. Oil pumps that maintained 60 psi at idle when most engines were happy with 20. Bearing clearances that seemed excessive but allowed for thermal expansion, contamination, and wear without failure. The engines would run on oil so dirty it looked like roofing tar. Not recommended, but they'd do it. The ignition systems were deliberately simple, points and condenser, not electronic. Why? Because you could fix points with a nail file and set gap with a matchbook cover. Try that with a failed electronic module in 1955. The distributors were weatherproofed like submarine equipment. One marine operator reported his engine running after being completely submerged in a hurricane storm surge. He drained the oil, changed the plugs, and it fired right up. But perhaps the most impressive feature was field serviceability. Every part was accessible. Every component could be rebuilt with basic tools. Head gasket job, 2 hours. Rod bearing replacement, do it with the engine in place. Complete rebuild. A competent mechanic could do it in a weekend with parts that any industrial supplier stocked. Compare that to competitors that required special tools, factory training, or worse, complete removal for major service. The economic impact was staggering when you did the math. A Chrysler industrial engine might cost 30% more than a competitor up front, let's say $3,000 versus $2,300 in 1954 dollars. But if that engine prevented just 1 week of downtime over 5 years, it paid for itself. And these engines weren't preventing 1 week of downtime, they were preventing months of it. Companies that switched their entire fleets to Chrysler Power reported maintenance cost reductions of 60% or more, and insurance companies took notice. Equipment powered by Chrysler industrial engines commanded lower premiums. Banks would finance equipment longer if it had Chrysler Power. Rental companies preferred them because renters couldn't break them. It was a reputation that transcended specifications, marketing, or even logic. These engines had achieved something rare in industrial equipment: trust, nen. The stories from operators became legendary. A logging company in Oregon had a Chrysler-powered yarder that ran for 30 years on the original engine. Not 30 years of occasional use, 30 years of daily operation in the worst conditions imaginable. Dust, rain, snow, running at full power dragging massive logs up mountainsides. When they finally retired the machine, the engine was still running fine. They sold it to a sawmill where it ran another decade, powering a head rig. A mining operation in Arizona had perhaps the most impressive story. Their Chrysler-powered generator provided electricity for an entire copper mine. It ran continuously, and I mean continuously, for 7 years. 24 hours a day, 7 days a week, 365 days a year. They had a backup generator, but never needed it. Maintenance consisted of oil changes, filter replacements, and 1 set of points. When they finally shut it down for a full inspection, the mechanics found wear measurements still within factory specifications for a new engine. And the marine applications developed their own mythology. Commercial fishermen are notoriously hard on equipment. Salt water, overloading, minimal maintenance, and the attitude that if it's not broken, run it harder. Chrysler marine engines thrived in this abuse. One documented case involves a charter fishing boat in Florida that ran the same Chrysler engine for 40 years. 4 decades of salt water, full throttle runs to fishing grounds, and maintenance that consisted mainly of hosing it off, occasionally. When the boat was finally scrapped, the engine was still running. The owner sold it to another boat where it ran another decade. But the real test came from an unexpected source: industrial refrigeration. Refrigeration compressors place unique demands on engines. They run at constant speed, under constant load, with zero tolerance for speed variation. Any fluctuation affects cooling capacity. Most engines required extensive modification for this duty. The Chrysler industrial engines worked perfectly right out of the crate. The massive rotating mass of those overbuilt components created a flywheel effect that maintained rock-steady RPM. Food processing plants, cold storage facilities, and ice plants became major customers. The numbers tell the story. By 1960, Chrysler industrial engines powered an estimated 15% of America's stationary industrial equipment. Not bad for a company known for cars. But more impressive was the retention rate. Once a company bought Chrysler power, they rarely switched. Brand loyalty in industrial equipment typically ran about 40%. For Chrysler industrial engines, 85% on the engineering philosophy influenced other manufacturers. Suddenly, everyone was advertising ours heavy-duty and ours industrial-graded engines. But most were just upgraded automotive engines with bigger bearings and better cooling. They missed the fundamental lesson of the Chrysler approach. Start with overkill, then add redundancy, then make it serviceable by a drunk mechanic with a hammer. That's reliability. Then competitors tried to reverse engineer the secret. They tore down Chrysler engines looking for exotic materials or revolutionary designs. They found neither. Just conventional engineering taken to absurd extremes, bearing surfaces that could handle 3 times the load they'd ever see, cooling capacity for running in hell, oil systems designed for combat angles. It wasn't any one thing, it was everything, overbuilt together into a symphony of unstoppability. The influence extended beyond direct competition. Engineers who worked on these engines carried the philosophy forward. Design for the worst case, then double it. Simple and strong beats complex and efficient. If it can break, it will break, so make it unbreakable or fixable with a wrench. These principles influenced a generation of industrial equipment design, but perhaps the most lasting impact was on the operators themselves. These were people who learned that equipment could be reliable, that engines didn't have to be temperamental, that you could buy something and trust it absolutely. This shifted expectations across the entire industry. Suddenly, customers demanded better. Why should they accept frequent failures when Chrysler had proven it was unnecessary? The economic implications were profound. Reliable equipment changed project planning. Construction companies could bid jobs with tighter margins because they knew their equipment wouldn't fail. Pipeline companies could promise completion dates and meet them. Mining operations could run with fewer backup systems. The ripple effects touched every corner of industrial America. Let's talk about specific innovations that made these engines so bulletproof. The block casting was extraordinary. While competitors used standard automotive casting techniques, Chrysler industrial blocks were cast with nickel content that added 40% to the cost but doubled the strength. The cylinder walls were thick enough that you could bore them 125 inches over and still have more meat than stock competitors. One rebuilder reported boring a block 200 over after a catastrophic failure and running it another 20 years. The crankshafts were forged from 5140 chromium steel, the same alloy used in aircraft landing gear. The counterweights were so massive that the engine would continue running smoothly with a completely dead cylinder. The main bearing journals were larger than some competitors' entire crankshafts. One engineer calculated that the crankshaft alone could handle 1/200 horsepower. In an engine rated for 150, the camshafts were equally overbuilt, cast from chilled iron with lobes hard enough to cut glass. The profiles were conservative, low lift, long duration, designed for torque, not horsepower. But those conservative profiles meant the valve train would last forever. No radical acceleration rates to break springs, no extreme lifts to wear guides. Just smooth, steady operation for decades. And even the gaskets were special. The head gaskets were copper asbestos composite that could handle 300 psi cylinder pressure and 300-degree temperature differentials. They'd seal even with warped heads or damaged surfaces. One mechanic reported reusing the same head gasket 5 times during field rebuilds. Try that with any modern engine. The fuel systems deserve special mention. While everyone else was going to complex carburetors with multiple circuits, Chrysler stuck with simple single-barrel or two-barrel designs. But they were perfect for industrial use. Huge throttle bores that wouldn't clog, simple float designs that worked at any angle, mixture circuits that could handle everything from kerosene to crude oil in an emergency. Operators reported running these engines on drain oil mixed with gasoline when proper fuel wasn't available. Not recommended by Chrysler, but the engines didn't care. The electrical systems were similarly overbuilt. Generators rated for twice the output needed. Voltage regulators that could handle reverse polarity, overvoltage, and dead shorts without failing. Starters powerful enough to turn the engine with hydraulic lock. Wiring with insulation rated for 400 degrees. One operator reported his engine still running after a fire melted everything plastic in the engine compartment. The wiring insulation was charred but intact. But the real genius was in the details nobody saw. The oil drain plugs were massive, 3 to 4 inch pipe thread, instead of the typical 1 to 2 inch. Why? So they wouldn't strip out when some gorilla with an impact wrench over-tightened them. The freeze plugs were brass instead of steel, so they'd pop out before the block cracked if the coolant froze. The rocker shaft supports on overhead valve versions had twice the bolts needed because bolts are cheap and downtime isn't. Non-testing procedures at Chrysler were legendary. Every industrial engine ran for 100 hours at full power before shipping. Not a quick run on a dyno, 100 hours at rated RPM and load. They'd deliberately contaminate the oil with sand to simulate dusty conditions. They'd restrict the cooling system to simulate clogged radiators. They'd run them at angles that would starve normal engines of oil. If an engine showed any sign of distress, it went back for analysis and improvement. The company's service network was equally impressive. Chrysler industrial dealers weren't car salesmen playing with big engines. They were industrial equipment specialists who knew these engines inside and out. Factory training was intensive and ongoing. Parts availability was guaranteed for 25 years, minimum. You could get parts for engines built in the 1940s well into the 1970s. Compare that to competitors who orphaned designs after 5 years. And customer service stories became legendary. A contractor in Alaska had an engine fail 200 miles from the nearest road. Chrysler had parts flown in by bush plane and sent a factory technician to help with the rebuild. A marine operator in the Caribbean had a crankshaft problem. Chrysler air freighted a complete rotating assembly and had a tech waiting at the dock when the boat arrived. This wasn't standard policy, but it happened often enough that word spread. Chrysler stood behind their industrial engines like no one else. The influence on American industry was transformative. These engines powered the construction boom of the 1950s and 60s. They built the interstate highway system, pumping concrete and running generators. They powered the oil boom, driving pumps and compressors in fields from Texas to Alaska. They kept America's food cold, running refrigeration systems from farm to table, silent, reliable, forgotten heroes of industrial progress. And modern engineers studying these engines are amazed by the purposeful overengineering. In an era of cost-cutting and planned obsolescence, the Chrysler industrial engine philosophy seems almost alien. Build it to last forever? Size components for 3 times the expected load? Designed for the worst possible conditions? Today's MBA-driven engineering would never approve such excess. But the results speak for themselves. There are Chrysler industrial engines still running today, 70 years after manufacture. not museum pieces, but working engines earning their keep. A generator at a ranch in Montana, a pump engine at a mine in Nevada, a marine engine in a fishing boat in Louisiana. They've outlasted the companies that built them, the dealers that sold them, and often the industries they were designed to serve. The lessons are profound. In our race toward efficiency, optimization, and cost reduction, we've forgotten something fundamental. Reliability has value, tremendous value. A machine that never breaks is worth more than 3 machines that do. A simple design that any mechanic can fix is better than a complex one that requires specialists. Overbuilding isn't waste if it prevents failure. And the Chrysler tank engine story also reveals something about American industrial character. When faced with a problem, needed tank engines fast, the solution wasn't elegant or sophisticated. It was brute force engineering. Take what works, make it bigger, stronger, tougher. Don't innovate for innovation's sake. Build something that works and keep building it until something significantly better comes along. And if nothing better comes along, keep building it for 40 years. The comparison with modern engines is startling. Today's industrial engines are marvels of efficiency. Computer-controlled fuel injection, variable valve timing, ceramic coatings, exotic alloys. They produce more power from less displacement with better fuel economy and lower emissions. But they also require specialized diagnostics, factory-trained technicians, and proprietary parts. When they fail, and they all eventually fail, repairs can cost more than the original engine. And it's when would a modern Chrysler tank engine derivative be competitive today? Probably not in conventional terms. Too heavy, too thirsty, too dirty for current regulations. But there's a market that would pay premium prices for that kind of reliability. Remote installations where failure means catastrophe. Military applications where simplicity saves lives. Developing nations where parts availability and ease of service matter more than efficiency. The philosophy, if not the specific design, still has merit. In the end, the Chrysler tank engine's greatest achievement wasn't powering tanks through World War II. It wasn't even the decades of industrial service that followed. It was proving a point that resonates today. Sometimes the best engineering isn't the most advanced or efficient. Sometimes it's the solution that simply refuses to quit. In a world obsessed with innovation, there's wisdom in remembering that reliability is its own form of genius. The story of how one Chrysler tank engine outsmarted every opponent isn't really about outsmarting at all. It's about outlasting, outworking, and outsurviving. While competitors chased specifications and efficiency, Chrysler built engines that would run when nothing else would. They didn't win by being better on paper. They won by being better in the real world, where dust and heat and abuse and neglect are the true tests of engineering excellence. And today, when you see construction equipment working through the night, generators humming at remote sites, or pumps moving millions of gallons, remember that somewhere in that mechanical heritage is the DNA of a tank engine that was too tough to die. An engine that proved reliability isn't just another specification, it's the only specification that matters when failure isn't an option. What's the toughest engine you've ever encountered? Something that refused to die no matter how badly it was treated? Drop a comment below and share your stories of mechanical immortality. And if you enjoyed this deep dive into engineering history, make sure to subscribe, because we're just getting started exploring the machines that built the modern world. These aren't just stories about engines. They're stories about the kind of overbuilt, over-engineered reliability that we've somehow forgotten how to value in our disposable age.